since one-to-one functions is our goal because we want to find inverses is what we want to get to, determining if a function is one-to-one is very important. And so you have the vertical line test, which is a perfectly good test. But there's also a second way to do it. And there's actually a second way where we can sort of force things to be have inverses, right? We have trig functions, but as it turns out, most of my trig functions are not one-to-one. And so what they do is they sort of do a little trick to force them to be one-to-one, and it's this theorem that does that. Alright, so one-to-one functions have inverses. Another way to, besides doing the vertical or horizontal line test, is determining if it increases or decreases changes. And so if a function has no turning points, right? So if it has no turning points and it increases over its domain, it's one-to-one then, because there's no place it's turning, and so therefore there would be no place where it would have a matching y value. Same thing if it was decreasing over its domain. Alright, then it's also one-to-one, because it has no place where it's turning around, like a parabola turns, right? One side's increasing and one side's decreasing. And so if my function doesn't have any turning points, and it's entirely increasing or entirely decreasing, it's one-to-one, because no place can it turn around and hit the same y value. Alright, and so what we can do is we sort of use this corollary. Alright, this sort of gets us, well, we can force functions to fall in the one-to-one if I limit their domain to their increase or their decrease, and we do this for a lot of functions. Specifically, it's done all the time with trig functions, because basically most of my trig functions are not one-to-one. And so what they do is they pick a portion of it that's positive, increasing, not positive, and they force it to be into one. So they limit its domain. Alright, so this is different. If a function's increasing over an interval, not the domain, then it's one-to-one over that specific interval. Alright, again, same thing with decreasing. If it's decreasing over an interval, then it's one-to-one over that interval. And so what we can do is we can force one-to-oneness by limiting the domain to be just where it's increasing or just where it's decreasing. And we do this a lot in mathematics. Alright, an example would be going back to my parabola case. Alright, so suppose, remember we said x squared was not one-to-one, but it's increasing over the x is greater than 0. So if we limit it to that interval, we're limiting it to the interval 0 to infinity. Well, if I only graph the function starting at 0, so starting here doesn't exist at 0, so that would be at the 0, 0, and it's an open point because it doesn't exist. But anything bigger than that, so shooting off to infinity, so 1, 1 would exist, and then it would have that parabola shape. And so there's f of x, which equals x squared if x is greater than 0, and it is increasing on that entire piece from 0 to infinity. And so it's 1-to-1 on that piece. And if I wanted to find an inverse on that piece. Now, it's not invertible everywhere, but only on that piece. And so we would be able to find its inverse limited to that part of my function. So we're just going to kind of look over a few examples determining if they're one-to-one. If they're not, can we determine where they're increasing and decreasing, where we could force it to be one-to-one. Alright, so the first example is a line, and so hopefully you recognize that a line is one-to-one. Alright, it is one-to-one if you graph it to test it out. 1-to-1. Alright, a linear function, so it goes to the 0, 5, and then it's increasing because it's got a positive slope. And so there's f of x. Alright, it is one-to-one, it passes the vertical line test, and it increases on its entire domain. Which means it has an inverse. Right? It will have an inverse. I can find an inverse. Right, part B. Right, it's the x squared function. It's not inverse. It's not one-to-one as is. So it's not one-to-one on its domain. But I can force it if I look at the intervals of increase and decrease. Alright, so this is the x squared function that's been reflected over the x-axis and shifted up 5 units. And reflected, and so it's opening down. And so if I look at this function, so there's my g of x. If I limit it to x greater than or equal to 0, right? If I look at it from x greater than or equal to 0, so 0 to infinity, then g of x is decreasing on that entire piece. So I could find an inverse. So g of x is 1 to 1 from 0 to infinity. Or if I wanted to do, I could look at the increase. And so if I limit g of x to less than or equal to, so on the domain negative infinity, 0, and a lot of times we'll include the turning point. We could include it or not include it in this example. I'm choosing to include it. The last example, the previous one, I didn't. And either way is fine. Whether you include, we usually typically do include the starting point just because it makes it easier to do that. But you don't have to. Alright, so over this piece, so that's this piece right here, right? From negative infinity to 0, g of x is increasing, right? From negative infinity to 0. And so that means it is 1 to 1 over negative infinity to 0, and therefore we could find the inverse, and it would be a different inverse over that piece, and it would be over, so I would get two different inverses, right? This would give me an inverse, and this would give me a different inverse, because I'm looking at different parts of my function. I'm looking at a function that's increasing versus a function that's decreasing, and I would get two different inverses in those cases. Alright, next example. So this is the square root function, where I've been shifted to the right 2 units, right? And so yes, it's 1 to 1 on its domain, which would be 2 to infinity. Now if you graphed it, right, it's been shifted over 2 units. That square root function shifted over to the point 2, 0, and then it's a square root function. So there's r of n. And yeah, it passes the vertical line test. So and it's increasing everywhere. It's increasing on its domain. There go 1 to 1 everywhere. And I can find an inverse on its domain. Alright, the last example before we get to inverses. H of t is t divided. So first of all, t cannot equal 0. And this one is 1 to 1, but I'm going to graph it. If you remember, this is the graph of this. It has an asymptote at t equals 0, which is the x equals 0, and at y equals 0, right? Because the denominator's degree is bigger than the numerator's degree. And if you graph it, it has this shape. It approaches both my axes, but never ever crosses either one of those axes. And so yes, it passes. So it is 1 to 1 on its domain, which is negative infinity to 0, asymptote at 0, so it doesn't exist. And so that means it should be increasing or decreasing, right? And it's decreasing, right? Moving down, right? And so it decreases on its domain. For some reason, this one's harder for students. They don't notice that these are both decreasing pieces. I'm moving down in both directions. All right, I'm shooting down to negative infinity here. I'm coming from infinity and approaching 0 until both of them are decreasing. Right. And so it's 1 to 1 and therefore has an inverse. All right, so that was practicing determining when functions are 1 to 1 and increase and decrease. And next we're going to get into inverses.